these diagrams represent the stages, okay? And then in the stages, you can kind of see the apple trees and how the apple trees are growing in number, but also around the outside, you can see how the number of evergreens is also increasing, okay? Okay, so when we work through this, our question is, when is the number of apple trees going to equal the number of evergreen trees? Okay, that's our question. Okay. And so one of the ways that you could continue to do this is by drawing all the pictures until you count up that they match, right? We're not going to necessarily do that. I was like, that's like the whole point of this lesson. Okay. What I want you guys to kind of figure out, okay, is using the table of values. Okay. I'm going to pull up the pictures here. Let's see. Okay. So, number of rows I think is going to indicate the stage number. Okay. And then we're just going to mark out how many apple trees there are. Okay. And then how many evergreens. So, we're just going to assume the number of rows is going to be the N1, N2, N3, N4, N5. Okay. And we're just going to see what's happening here. Okay. So, let's take a look at the number of apple trees. Okay. In each of these pictures. So, we're going to go, okay, well, number of row. Okay, so stage number 1, it looks like we have, here, I'll make this a bit smaller. Stage number 1, it looks like we have 1 apple tree in the middle. Okay, stage 2, we have 4. Stage 3, we have 9. And stage 4, we're going to have 16. Okay, and then let's look at the other one, okay? In the number of evergreen trees around the outside. So the evergreens is going to be 9 in the first one, okay? Then we got to figure out how many are in this one. 1, 2, 3, 4, 5. There'll be 5 along the bottoms, 10. And 3 here, 3 there is going to be 16. Okay, so a little 1, 2, 3, 4, 5, 6, 7, 14. 14 and 10 more should be 24. Is that right? Okay, I think that's right. And then the last one, we're going to see 1, 2, 3, 4, 5, 6, 7, 8, 9. So 18 and 14 should make 18 and 10 should be 28, and another 4 should be 32. Did I miscount the first one? I did miscount the first one. Did miscount the first one. Okay, so there's 3, 6, 7, 8 in the first one. That should help clarify things. Okay, just gonna check the chat here. Do we have any issues? Okay. Now, I want you guys to take a look at, if we drew, just to highlight what it is we're doing, okay? If I wrote 2 tables here side by side, then I go 1, 2, 3, 4, right? I'm going to do number of rows and the number of apple trees here first. Okay, I'm just going to write 2 tables of values where I have like X and Y. Okay. So in row 1, I'm just going to copy this data. Okay. And then underneath I'll do it in black underneath here for same number of rows, right? 1, 2, 3, 4. And then beside we're going to go 8, 16, 24, and 32. Okay, I guess my question is going to be to all of you. Okay. And then I'd probably start here. Could we figure out, you guys take a look at which one of these 2 would you start with in terms of trying to fill out the rest of this? one's, I know the answer, so it's hard for me to like say which one's easier than the other. Okay, but I guess our question is going to be how many like apple trees are going to be in stage 5, right? Versus how many evergreens are going to be in stage 5. Remember what I've done here. The black is going to be the evergreens, right? And the red table is going to be the number of apple trees, okay? So I'm going to give you guys a sec here. Try and figure out in this table what all these numbers are, okay? And then we'll go down there and plot them. Okay, what I want you guys to check right off the top. We should recognize, well, I want you guys to get in the habit of always just checking these first differences, okay? In both of them. Okay, it's not like an explicit, so it only works for one and not the other. Check it for both of them. Okay? And see what you get. What you're going to notice is one of them is going to be a little bit more convenient than the other. Okay? So when I check the first differences in, like, let's say the black table, okay, so all the number of evergreens, if I check this, here I'll do it a different color. Okay, how do I get from one to the next one? Okay, is the question. Well, it looks like to get from 8 to 16, I have to add 8. Okay. Well, if I go from 16 to 24, I've got to add 8. And I go from 24 to 32. Well, something interesting happens there, right? Well, it's these match. Right? I've got to add 8 each time. That sounds like a line. If I'm adding 8, that sounds linear to me. Adding 8 each time. So then I can go over to the table, right? The evergreens. And you can write out, okay, well, for 5, stage 5, in stage 5, you can add 8 to 32. We're going to be at 40. Right? And then we can add another 8. Okay, to 48. But before we get carried away, I could probably, because you guys already know how to do this, come up with an equation that represents how the number of evergreens are changing, right? Which might ask us that down. Okay, it doesn't. So we could write an equation that represents, and I'll write it in black so we can like distinguish between the two. Okay. If you remember from the break, before the break, when we did all the linear patterning, we always take like stage number, and it looks like we're taking that stage number and multiplying it by 8. 3 times 8 is 24. 4 times 8 is 32. 1 times 8 is 8. So it looks like if I were to write y, so the number of trees is going to be y equals, right? Well, we're going to take the stage number, x, and we're going to multiply by 8. That's the equation that represents this data set. And this is a line. It's a line because we showed through the first differences that they matched, and therefore it is a line. Okay, so we can continue going under these using this equation or adding 8. So 48 and 8 is going to be 56. And another 8 is going to be 64. And you can confirm that because 8 times 8 is equal to 64. Okay, so that I know I'm right. And then you can also check 9 times 8 should be 72. Okay. So if I go down to my table here, or my graph, sorry, and I'm going to try and plot these points now. Okay. Well, this relation, remember, if we write y equals mx plus b underneath here, there is no starting value here, right? Based on the equation that we wrote here, it's plus 0, right? It's plus 0 because you guys remember too, if we found the first differences, how do I get back to the 0? Remember, if I'm going 5, 4, 3, 2, 1, 0, to get back to the 0th term, or the starting value, I would have to subtract 8. Well, 8 minus 8 is going to be 0. Okay? And so that's how I know that the starting value, b, is 0. Okay? So then I can plot that line. We know how to do that too. Okay? Or you can plot the points from the table. Okay? So 0, it's going through 0, 0. Okay? And then at stage 1, we're going to go up to 8. This is going to be a little bit rough just because we're guessing at some of these values. 2 is going to be 16. 3 is going to be 24. 4 is going to be 32. So on and so forth. Okay. Well, we could keep plotting. Okay. Now the challenge here, okay, that's not necessarily the challenge of this question. It looks like, and this is what's so great about this question, is it looks like we're going to set up two systems or two lines and then find where they intersect, right? Like what we were talking about yesterday to a T, right? And then we talk about the point of intersection and what that means. Okay? Something interesting happens with this question in particular, though. Okay? So if we turn our attention from the number of evergreen trees, okay, so this column, I want to turn our attention to the number of apple trees. Okay? And so what I'm going to do, just going to try and clean this up a little bit. What we're going to try and do is figure out how this pattern in the red, or the number of apple trees, is changing. Okay, so if I take a look at doing the first differences in this table, okay, it looks like we're increasing by 3, increasing by 5, increasing by 7. Well, these do not match. Okay, so this looks like our cup question, right? Like the first differences don't match, which means our graph for this series of points is not going to do anything like this. It's not going to be a straight line of any sort, right? Which we saw with the cups. Okay, which means, okay, well, if it's not linear, then you better check what it is. Okay, so let's do it again, except this time we're going to label the second differences. Right? Then we're going to check it again. Okay, well, it's increasing by 2. And then from 5 to 7, we also get 2. Well, now these match. So we know it's not linear. It's quadratic. Okay? So our job now is going to be to figure out the rest of these values so that I could plot the points, right, and see what's happening. Okay, well, we need to find a relationship from here to here. Okay, so I don't know, how do I get from 1 to 1? Well, that's kind of an easy one. But from 2 to 4, right? Some of you might say, okay, well, I'll multiply by 2 to get from 2 to 4, right? But remember, whatever rule you decide on here, it has to work for all of these points, right? And so the issue with multiplying by 2 is when I go to check, even the next one, 3 times 2 is 6. That's not 9. Right? I need it to equal 9. But it doesn't match. So, okay, well, we're back to the drawing board then, right? Because our rule doesn't work. And this is where the quadratic gets its shape and really defines it as a quadratic, okay? I'm just going to go ahead and describe it to you. The rule, okay, if you guys remember, like if we just treat like y equals, this is like number of cups. And then, and then this is, x is going to be stage number. The thing with quadratics is they always involve an x squared. Okay, and this is the direction that we're headed. Okay, so they're a little bit more complicated. So if you guys can confirm, if I take stage number, or number of rows, and I square it, I'm going to get the number of trees for all of these. Okay, so I can confirm that. 1 squared equals 1. 2 squared equals 4. 3 squared equals 9. 4 squared equals 16. 5 squared is going to equal 25. 6 squared is 36. 49, 64, 81. Okay, now what I want you guys to do is to plot these points again and see what happens. What you're going to find is the interesting part of today's lesson. What a quadratic actually looks like. I've shown you how to prove if something's quadratic versus linear, but I want you to be able to actually produce the graphs and tell me what it looks like now. Okay? So, what we're going to see, we're just going to go plot these points. So 1 and 1 is going to start somewhere around here. Okay, it's pretty low. Okay, and then we go 2, 4. And then we go 3, 9. So that looks kind of linear at the moment. Okay, just based on the first few dots that I drew. And obviously, if you're at stage 0 with a quadratic, 0 squared is equal to 0. So you could put that in there too. It kind of starts there, right? If you're at stage 0, they haven't planted any apple trees. Okay. 4 squared is going to be 16. We're starting to see that it doesn't really look, it's starting to look not linear now, right? There's a little bit of curve going on there. Right? And 5 squared is going to be 25. 6 squared is going to be 36. 7 squared is going to be 49. 8 squared is going to be 64. And then 9 squared is going to be 81. Okay, so if I connect these dots, right, what we're going to see is something that doesn't necessarily look linear. This is what we define as a quadratic, the graph. Okay. You guys can also answer one of the questions that we asked from the very beginning. When are the number of trees equal? When are they equal? That's like the point of intersection between these two graphs. Where do these cross? Right here. What is this point? 8 and 64. How do I know it's exactly 8 and 64? Because if I look at stage 8, both number of trees are 64. Okay. So again, you can see how long that would have, well, how long it took us to do the table of values, right? And there, I wouldn't necessarily say that there's an easier, at least for you guys, not an easier way to do this aside from actually figuring out the point of intersection between a quadratic and a line. You're just going to graph them and figure it out. But it's doable. Okay, so this is kind of an interesting question from the standpoint that hopefully, if you were here, you can kind of see the relationship between what we have been spending 2 or 3 days on with lines and finding intersection points. Okay, but now I've incorporated a different kind of graph that is not a line. But the concept still applies, and this point means something. It's the point at which the number of trees are equal, because the two graphs cross. Okay, so for stage 9, there would be more apple trees than evergreens. Remember, the blue represents apple trees. On stage 9, there's more apple trees than there are evergreens. Right? The opposite is true for all of the stages below 9. So again, we're just looking at the fact that this point of intersection is a decision point. And the difference between this and the stuff that we have been spending our time doing is that the blue line is not a line anymore. Or sorry, the blue line, the blue graph is not a line. But the black graph is a line, which can be modeled by this. Okay? So, one more question. So we kind of answered, how can you show the answer to the problem on the table of values in the graph, right? What we see here on the table of values, that the number of trees match. Okay? And on the graph, we just talked about the decision point, or the point of intersection. Okay? That's how we can tell in both of these instances. Table values or the graph. Graph is the point of intersection. Table values is where the numbers are the same. Okay? That's it. Okay? Just give me a sec here. We'll stop the video.